Benc, working for Red Hat in the Czech Republic, and mostly working with vSwitch and similar stuff. So this presentation is about what I found when I was trying to debug some cloud network related stuff, and that led me to some thinking and gathering some information about that and so on. So could you please close the door? Guys, could you please close the door? Thank you. So, first thing is probably we should define what we mean by cloud networking, or what's the difference between traditional networking and cloud networking. So, cloud networking is a thing that you have multiple virtual machines that want to talk to each other, and you basically want to emulate to them a local area network. So you have that large company that has its infrastructure offloaded to a cloud, and you have its direct competitor in the same cloud, and both of them have multiple machines that are virtualized, and they want to talk to each other over local network, but they don't want to see each other. You don't need or don't want your customers to see each other private data. So those virtualized local networks are called tenant networks, and the important concept is isolation of different tenant networks, and at the same time interconnection, because you want those computers or virtual machines to access internet and access publicly available services from the other tenant networks. All this stuff leads to pretty complex virtual topology, we'll talk about it later. It really doesn't matter what technology you are using, what is underneath, whether it's OpenStack or Kubernetes, Docker. All of these things are solving or will be solving shortly the same problems. So what happens when you SSH, you are an admin of the data center, you SSH to one of the physical machines, and you look there, what's there. So what you see is just several tens of different network interfaces, both physical, like physical cards connected to the machine, or virtual, meaning virtual interfaces connected to virtual machines. All of this stuff is connected into bridges with some really weird hierarchy. The bridges could be Linux bridge or OpenVSwitch or other virtual switches. And this stuff is also connected with so-called VTH pairs. That's some kind of link between two different bridges or namespaces or whatever. And the stuff is in different namespaces. You can have one bridge in this namespace, other bridge in that namespace, and like that. So it's quite complex. Well, if you look into that with ifconfig, good luck. You won't see most of the stuff. You can, of course, use more modern tools like IP or ETH tool or such stuff to discover what's the setup on the machine. But you will have to run that, several times with different options, different tools, take notes on a piece of paper, combine the data together. I mean, the information is there, everything is there, but it's scattered. You need really output of different tools. The relations between those different links, like which end of the VTH pair is linked to which, it's really hard to find. And figuring out the relations can be quite challenging from time to time. And to make the things worse, most of those tools are not namespace aware, so you have to actually switch to the namespace you want to gather data from and so on. The tool that we use in RHEL, for example, SOS report, which is supposed to grab as much information about the customer setup as possible. That's completely namespace unaware. So if you have, for example, OpenStack and SOC port, it's completely useless.
I know.
To make this worse, there are quite different situations when you don't have direct access to the machine, like SSH. You are debugging a problem at the customer side, but the customer is refusing to give you access. He is quite willing to give you any information you ask for. But that means you ask him, okay, send me output of IP and NetNS list. Okay, please send me output of IPA for all of these network namespaces. Okay, please send me ETH3 output for these particular interfaces in those namespaces, and so on. So it's like 5 or 7 iterations until you gather all the data. So this is not the way to go. So this led to creation of a really quite simple tool that you can just put the machine, run it, it scans the configuration of the machine and outputs or plots a graph or diagram listing, showing what's connected to what. It has no dependencies or almost no dependencies, so you can just grab the binary SCP to the target machine, run it. It outputs dot or some, it outputs a dot file to standard output, which is a language that understood by several different programs like Graphis or Graphizi and so on. And the result is nice, hopefully nice looking graph. I will show you. So this is the URL, and no. Well, okay. Okay, yeah, now. So this is the sample output. This is, I will zoom that out. This is a really real life use case. That's OpenStack Neutron machine, or OpenStack machine configured by Neutron. And all of those green boxes are interfaces. Those arrows is the connection. So this example is OpenVSwitch bridge. Has many interfaces connected to it. Those are access ports and so on. So you see, even with this tool, it's quite complex. But at least now you can figure out what is connected to what place and what relations are. So, okay, yeah, that worked. Let's look at a somehow stripped down diagram that is to understand, and we will look at what the poor Neutron guys were actually forced to do because of the requirements they have, and the kernel not being exactly, or the tools not being exactly prepared for these cases. So everything is possible with Linux, as you know, but sometimes it's like scratching on your right side with your left hand. So this thing is just a central point of the setup. That's the so-called integration bridge. It's an OpenVSwitch bridge, which most of the stuff is connected to. So let's look at this part. We'll just look at all those parts one after other. So I will zoom it in. You see the integration bridge here. And now this is here it's virtual machine. This is a chat interface connected to the virtual machine. And this interface is connected to a Linux bridge together with one side of the ETH pair. The other side of the ETH pair is connected to the integration bridge, and it's tagged this is an access port, meaning the traffic that goes this way receives or is assigned a VLAN tag. Well, so first, if you don't know what VTH pair is, it's some kind of pipe. So whatever enters this interface, it is received on this one, and vice versa. So the traffic from the VM goes through the tap device to the Linux bridge, then to the VATH device. It's forwarded to the other side of this pair, and then it's sent to the Open vSwitch bridge. Why is that? Well, the reason is simple. They need to control what the virtual machine sends. Do some things like anti-spoofing, meaning enforcing that the machine only uses the IP address it was assigned, and such stuff. If they connected this thing directly to the bridge, well, it's bridged, no firewall. So Linux bridge actually allows filtering. That's so-called EB tables, Ethernet bridge tables, and that stuff is able, or that the thing is able to call into IP tables. So you can do some advanced filtering. EB tables can do some basic filtering. IP tables is more powerful, basically. So they can do in this way. They can do here between those two lines. They can do filtering. But they cannot attach the bridge directly to the Open vSwitch. So they need this thing to help them. So let's look at another part. There's one. Again, integration bridge. This thing, this box, is a namespace. It's network namespace. That's basically that means that the interfaces inside are isolated from the rest of networking interfaces. Are isolated from the rest of the networking interfaces in the system, and they get some kind of private networking stack, meaning custom routing table, custom IP tables, rules, and so on. So here they have interface that's Open vSwitch internal port, which is put into this namespace, and the traffic that comes out is routed in this namespace to this interface. It's the IP routing, so there is a route table configured with proper rules and so on. And then this is another Open vSwitch port of this bridge. So the traffic, once it's routed, is outputted to this bridge, and this will be generally connected to a physical interface, so the traffic goes out of the machine. Why are they doing that? The reason is that here, between those two interfaces, they can do network address translation. Yeah? That's simple. They can do also firewalling there using IP tables. So yeah, they need that. They need actually, I said that it's a local network, so it has private addresses. They need to be usually translated to a publicly visible address. So yeah. Next part, there is one. This is a way to connect to data center network. Means it's a network that is local to the data center. It's not visible from the outside. It connects different physical machines. So the communication between guests in the same tenant network is fast, even though those virtual machines are connected on different physical machines. So yeah. So what they do is this is the physical interface connected to vSwitch, and that vSwitch is connected with the integration switch using VATH pair. The reason is that the VLANs used to isolate tenant networks on this physical machine, so the VLAN numbers may be different than the VLAN numbers that are used in the data center network that interconnects different physical machines. So there will need to be a translation between those VLAN numbers, which is done here on this vSwitch. Open vSwitch is capable of doing that, but it has to be isolated from this bridge. So that's basically the reason. And the last part, the last interesting part of this diagram is this one. And that's used to run pertinent programs like DHCP server or DNS server. This is again namespace. There is a single interface in there. The program that runs in this namespace is attached to this interface only. It doesn't see any other except local one, of course. And this is an access port integration switch. Tag with tag 1 in this example. That means that only those virtual machines that have the same tag sees the traffic. Why it's in namespace? That's because the different tenant networks can have the same internal IP addresses, the same range. So you have to, if this interface was root namespace, then basically this particular IP network would have to be assigned to this particular tenant only, which wouldn't really work. There's also more stuff that's needed or will be needed in the future or is needed and is currently being implemented. And those various stuff. And that's QoS, quality of service support, meaning different virtual machines can have different bandwidth allocation. IPv6 support, that's mostly important for various tunneling things. IPv6 tunneling for example, in OpenStack is currently not supported. Various VPN connections and so on and so on. So there's quite a lot of interesting stuff going on. Well, so the problems or the challenges faced are solved by this setup. But this setup has some problems and some really bad problems, I would say. But the most obvious one is performance. If you remember that what the packet from the virtual machine to the integration switch, what it has to go through, that's IP tables and EB tables. IP tables, they are quite optimized, but still they have performance penalty, which is quite measurable. EB tables, that's performance nightmare. That's really slow. So they have a bridge, and the packet has to go through both EB tables and IP tables. And then VTH pair. VTH pair means the packet is received on one end, it's put into backlog in the kernel, then it's processed in another soft IR2, and then it's received. So that means more processing of the packet in the kernel, more CPU usage. The backlog itself has limited length, so if the CPU is slow, you get packet drops. Of course, you get more latencies. You have more queue involved, more queues involved, and more CPU processing involved. Bridge, yeah, it's a similar story. More latencies, packet drops, more CPU usage. vSwitch, yeah, again, and so on. Even such thing, at the first sight, simple thing, like moving a packet from one namespace to another. It's not cheap operation. You have to actually zero the metadata, some metadata in that, and to do proper accounting, and yeah, it's not free. So combine all of that together, and then if a packet goes from one VM to another, goes through all of these twice. So performance, yeah. Another problem is misuse of bugs. I showed that stuff that OpenVSwitch port is connected to, or is put into a different namespace. Remember that pertinent programs, for example. That's nice, except it doesn't work. Well, it does somehow, but it's a lie. The fact is that OpenVSwitch is completely namespace unaware. The bridge, the vSwitch bridge, together with all ports, is supposed to be in a single namespace. But there is a bug in the kernel which does not properly prevent moving the ports to different namespaces. Well, those guys discovered that. They are using that now, so we cannot just disallow it now. Yeah? But the thing that are required from passing the packet from one namespace to other, they are not done in the kernel in this data path. So yeah, it works only with luck. So that's another problem. And then there are more obvious problems like debugging. If you have such a complex setup and you log into the machine, which was my case, well, yeah, debugging why the hell a packet is dropped on this particular interface. That's really, really hard. And of course, complex setup means much more costly maintenance. So how to solve that? How to approach these problems? And as I said, I'm talking mostly about Neutron, but it's not Neutron specific at all. Any stuff or any technology that tries to solve this problem, which is similar to containers, to virtual machines, to Kubernetes, Docker, will have to face the same issues and will face the same limitations of the kernel and OpenStack and other tools. So what can we do? The firewall stuff. We need firewalling of the virtual machine traffics or container traffic. So how to approach it? We can use OpenFlow because OpenFlow as a protocol is capable of doing some filtering. It can match on different header fields in packets. It can drop packets. So far so good. Except that given the version of OpenFlow, the options you have are limited. So with the newest OpenFlow version, it's probably quite okay for the needs, for example, Neutron has. But at the time they were working on that, that version of OpenFlow that's available just did not have enough capabilities of filtering. So yeah, I think that they are now thinking about really moving these rules to OpenFlow. Or we can use something other. We can use TC, traffic control. That's infrastructure in Linux kernel that's mainly used for quality of service, like shaping. What's shaping? Well, you have packets, and you decide which kind of packets will go through with which priority. And if the traffic is going too fast, you start dropping traffic according to some rules. So you have rules, and you can drop traffic according to rules. That's firewall, basically. So in truth, TC, the infrastructure in kernel is quite powerful. It can do more actions than just dropping packets. It can do quite a lot of stuff, can modify packets, and so on. So, yeah, we can actually use TC for firewalling. And it's quite powerful stuff, or could be quite powerful stuff, if we implement some more things than are currently implemented, which, by the way, will be discussed at upcoming network workshops. So, yeah, there's some quite interesting things ahead. With this, we can get rid of this stuff and connect the top device directly to OpenSwitch bridge and do the filtering either inside the switch with OpenFlow rules or do it here at this interface with TC filters and actions. Next problem, network address translation. Well, in what I was talking about in the previous slide, the firewalling, it was mostly stateless stuff. So you filter on destination ports and IP addresses and so on. For network address translation, you need stateful firewall, meaning you track connections. This is currently not possible in OpenStack, but guys from VMware and Nicira, for Neural Networks, which is Cisco, and Nicira, which is VMware, guys are working on implementation of contract in OpenSwitch. With that, OpenSwitch will be capable of doing network address translation. So this would actually get rid of this stuff, and we could connect the interface going outside the physical NIC connected here directly to this integration bridge and get rid of this completely, which would be nice. I mean, look at that. That's two interfaces added. for each Tenant network. Next thing, as I said, Open vSwitch ports are not supposed to be put into different namespaces. So we have to do something with that because it's bug and it's abused bug, but it's abused in wild, so we cannot really discard that feature or this thing. So how to solve that? The obvious thing is using DLTH pairs to connect Open vSwitch to namespaces, so modifying OpenStack or Newton, so on. Well, yeah, that will fix the problem, but with the effect on performance, which we don't want to do. So we can let Open vSwitch be namespace aware and actually officially allow moving the interface or the internal ports to different namespaces. Disadvantage of that is that it will actually add some operations into this part, which will be executed even when this internal interface is not in different namespace. So it will have actually affect performance also for normal use cases. It may turn out necessary, but it's definitely not something to be taken lightly. Or we can create a special port type that is actually allowed to be moved to different namespace. Well, yeah, this is still something we're working on. Well, yeah, so this is the illustration of where the problem is. This is the Open vSwitch port that's in different namespace than the Open vSwitch itself. We won't get rid of that. This is actually the correct usage of namespace, or good usage of namespace. And yeah, this is how it was intended. So yeah. VLAN translation. How to do that? Yep. We can of course try to find out some clever OpenFlow rules that would allow the translation. I think it's possible. So yeah, that's one option. Another option is again TC. As I said, TC infrastructure is quite powerful. It can modify packet. There's absolutely no problem for TC to change the VLAN tag on Android packets and change it back on incoming packets. So yeah, I think that even works currently, right, Jiří? With your patches, I think it's even possible currently to do. That will mean getting rid of this stuff and connecting this interface directly to this integration bridge. Again, two less interfaces. Nice. QoS. I have no picture for that, but Open vSwitch does have QoS support, but it's quite limited. It supports only a few algorithms and a really limited set of options. So yeah, we can implement QoS support, more powerful QoS support in Open vSwitch. Sure, it's no problem in that. But we have to realize that we are duplicating something we already have. We have quite powerful QoS infrastructure in the kernel using QDisks and TC. Again, we can use that actually. So, yeah. You probably noticed that I was talking about TC quite a lot, and you can replace that with TC and that with TC. So now currently we have IP tables here and bridge and Open vSwitch, and maybe we will start using TC. So that's quite a lot of stuff. So couldn't we consolidate it somehow? I mean, having just the central bridge, the Open vSwitch bridge, and everything connects to that, and all the logic is in the Open vSwitch bridge. That's quite tempting. That should be quite easy. That would actually be quite easy to debug and look at with proper tools and so on. So yeah, we can do that. And actually, if we think about it, we can replace the whole kernel data part of Open vSwitch with something different, something more powerful. For example, with something based on TC solely. That's possible. This is quite couple. Or, which is probably more likely option, we can replace the kernel data path with EBPF. EBPF is some kind of bytecode that's interpreted in the kernel or JIT compiled in the kernel optionally, and you can basically program what should be done with different packets, where they should be forwarded to, how they should be changed, and so on. So you can replace the whole kernel stuff with eBPF. I mean the OpenStack kernel data path. Which, by the way, is thing that's maybe going to happen in several years. But it will lead to quite powerful things. If you think about it a bit further, do we really need vSwitch? I mean, we do not really use OpenFlow. We really do not need OpenFlow. Neutron is using OpenFlow because it's the way to configure vSwitch. But the main idea behind vSwitch is that you separate control data plane and then control that data plane from a different machine. We're not doing that here. We have a daemon running on the machine which is able to configure almost anything, and it has different backends anyway. Yeah, so why not? Do we need it? Cannot we use TC directly from the backend? Or cannot we use eBPF directly somehow? Why to translate what we need to OpenFlow rules and let vSwitch daemon translate it to eBPF rules if the data path is placed by eBPF? Why could not Neutron or Kubernetes or Docker just create eBPF programs by itself and upload it to the kernel? I'm thinking further was something we discussed actually this week with my colleagues. Couldn't we just rip off the whole networking stack and replace it with something with eBPF or something like that? It will solve a lot of problems actually. So a bit more seriously, I mean, I'm serious with those first two things. Yeah, not so much with this one, but yeah, who knows? But then the last one, there's a new project announced by VMware, Open Virtual Network. It's basically a layer on top of OVS. It's a bit more abstract. It works with networks, and it's basically doing all the stuff that, or much of the stuff that, much of the stuff that Neutron and such stuff is trying to do. So there's another option, using OVN, or perhaps implementing something like OVN but without OVS. We don't really need the OVS actually. So yeah. Well, that's about it. The options are open. If you have any ideas, just send them to me, to NetDev, to OpenVSwitch list. Let's think about the future and how can we improve stuff together. Any questions? No questions. I bored you. Okay, so down with questions. I thank you for attention. So you mean in the neutron or?
We were showing the details of this. We have to divide and show single parts.
To be honest, I don't know exactly why they chose this solution.
You have only one VLAN or VH, so you have VLANs and
It's one VTH per one physical interface. So you have multiple physical interfaces connected to the data center network. You get multiple copies of this stuff of VTH per second.
you have VLANs transferred
This is traffic that's actually going between those physical machines. So if you have one Tenant network spanning multiple physical machines, which is quite usually. It's mine.
Yes, I saw so.
Then you need those machines to communicate somehow. And usually you have fast local network and slow internet connection. So you have a separate network for the data center, and this is used for this, for basically actually for two different VMs that belongs to the same internet network on two different physical machines to connect with each other. The point is the VLAN mapping on those. For example, in this machine, it has VLAN tag 1. In this machine, it has VLAN tag 3. Yeah? And this is that's neutral for us. The OpenStack.
so you don't see the VLANs.
You see VLAN here. You see VLANs here. You see VLANs on the data center network. The packets are tagged with VLANs. And that's,
They are untagged.
they are unchecked. They are retagged.
So this bridge doesn't see the VLAN tag. You just see an interface.
It see the VLAN tags from the outside, okay, and it retags them to the
This bridge
interface.
actually does.
Yes, this bridge does. That's the purpose of the bridge.
I don't understand the VA.
Yeah. This is for actually connecting these two bridges together.
Just to have the interface in between.
Yeah. They probably do more stuff there. Yeah, I simplified a bit because I mean,
This VH prayer is
40 minutes.
like, we didn't want to do the difficult stuff, so we just be here.
So, yeah. Yes. Dobrý, ne? It worked for me. You just switch to the external output now.
I have switched to external output and
I don't know, my actually with the new kernel and new other it checks the connection, but my old laptop I have to switch manually, so I don't know.
VGA1 is connected. Okay.
VGA connected. Okay, so yeah, so it checks. I don't know if it's used. Don't you have? It's not. Okay. Don't know.
Okay.
Connects to Windows machine.
I will just copy the presentation from there so I can go from the next step.